and then I'm out of it.
Okay, well anyways, let's talk today about motion down an inclined plane. Now an inclined plane is simply a fancy word for a ramp. Okay? So, if you look at the Manitoba curriculum, it says calculate the forces acting on an object resting on an inclined plane. Well, I'm going to show you that right away, including the normal force, friction, components of the gravitational force, and then you will calculate the components of F gravity exerted on an object resting on an inclined plane, and then you will solve problems with that. Okay, draw that picture. Draw that picture of a ramp. Make it nice and big. This part, yeah, draw the triangle part too. I think. Let me see. Do I want that? Well, you know what? Okay, yeah, go ahead and draw it.
You be the judge, Stephen.
I would say like a third of a page.
Oh, what?
Oh yeah, because we're going to be putting stuff on there.
Back it up. Wasn't that big? Not that big.
Or do you want to wait? Do you want to wait till I get to that actual? You may need, for those of you that have already drawn it, you may need to sort of back up when we get to that.
Okay, I'm still going to do it.
Okay. So anyways, when you got, what the app was going to show you was that as the angle here increases, what happens to this angle here? As the angle of the ramp gets bigger, what happens to the angle in here by the box thing?
It will get
Deeper? Like, if this was completely flat, if this angle here was flat, and there's your box, this one right here would be straight down, wouldn't it? And in fact, that angle there would be 0. What I'm really trying to say here is that this angle here is equal to that angle there. Does that make sense that those two angles would be the same?
Can you write that down?
It's up to you. Do you need to know it?
Do we need to know?
We need to know it. Do you need to write it down to know it or to remember it?
Are we just talking about where the arrows go?
Just, all I'm talking about is the angle of the ramp is equivalent to this angle in here. And you guys don't know what those arrows represent just yet.
That's confusing.
Okay, well, let me explain. Okay, so when an object sits on a flat surface, you've got a book, a can of Snapple,
that little triangle.
Snapple.
right there,
At the top.
right there.
I'm on there.
When an object sits on a flat surface, gravity acts downward, that's
This
FW.
is important. This is important.
Yeah.
Yeah, it is.
There's FW, and there is what we call the normal force. And when they're on a flat surface, they are balanced. Quinn, I need you to listen and stop playing whatever it is you're playing with my sticky notes, please.
It's my group table. So.
Okay, Ryan, are you doing this? You are? Okay. That's good. Just curious as to your choice of seating where you're completely facing the opposite direction. What happens when the surface isn't at an angle? If I take this whole thing and I do that, well, which way is gravity now? Like so, right? That is my weight force. Now I realize you can't draw that. Is this still the normal force here? What's the definition of the normal force? The normal force is the force that is... yes, that's what most people think, but it's actually perpendicular to the surface. Perpendicular, 90-degree angle to the surface. So the surface is pushing up this way, but gravity is pulling this way. Are they now balanced? No. When there are unbalanced forces, there is a which leads to a
Applied force.
which creates a acceleration. An acceleration. Which way is the acceleration?
Do we draw this picture?
Down. No, just watch. Don't worry about making notes. Worry about learning.
Oh, it's right. Okay.
The acceleration is down. This thing right here, I like to call FD. It is the force down the plane.
Oh, Lord.
And the greater the angle, the greater the FD. In fact, if you went all the way like this, the FD would in fact be
0.
100% gravity, right? There would be no normal force. Okay, but it's not. So, when an object sits on an inclined plane, gravity acts straight downward, Fw. So on that diagram that you already drew, there's your Fw, and the ramp exerts a normal force, Fn.
Right.
Okay? So this is Fw right here.
Was that part of the triangle?
Yeah, this is the one that you drew already, right? So the normal force is up, off the surface, and the Fw is down. Now, there is,
Ooh, what was that? Was that the angle? Okay, what's the angle?
Same
I'm just
angle.
kidding.
same angle there, same angle there, theta and theta. Oh, what did I just press?
Yeah.
Yeah. So this here is Fd, the force down the plane. Now, this force here, I label Fn. I am lying.
No.
You're right. Let me explain. The Fn in blue is the true normal force, right? This Fn here is the component of gravity that acts perpendicular to the plane, right? Because when it sat flat, the weight force and the normal force were balanced, right? But now they're not. See, you're not watching. Riley, you need to watch this. I'm explaining now, you guys. Listen now. Don't do other stuff. These two normal forces are equal to each other. This is the true normal force. This is the component of gravity that is perpendicular to the plane. Would you like to call it that? The component of gravity that is perpendicular to the plane. No, nobody wants to call it that. It's nerdy and it's way too long to say. We're going to call it Fn because it's numerically equivalent to the actual Fn, just in the opposite direction. Now that I have your attention, I'm going to explain that again. The weight force is down. The normal force is always, when it's flat, always straight up, right? Because we have an angle here. Part of that Fw pushes against the surface, and the other part pulls it down the plane. The greater the angle, the greater the Ft. In fact, the greater the angle, the greater the Ft, and which one gets less? The Fn gets less, right? So this Fn is actually the component of gravity that is perpendicular to the plane. Shorthand for that, abbreviation for that, normal force. These two are numerically equal, just opposite directions. They're equal, numerically. Like in other words, if Fn is 10, then this Fn down here is also 10. Now, how do we find those two? The quantities Fn and Fw are simply the components of the weight force. Now, up to now, we've had components x and y, right? Well, we're going to give that literally a twist. Okay? The x is like up and down the plane, and the y is perpendicular to the plane. That gets a little confusing, so I label this as d down the plane, and this is n, the normal force, perpendicular to the plane. It's just a labeling convention, that's all it is. Okay? I've sort of set the groundwork here. Some of you will get that, some of you won't. That's okay. Okay. Here's the important part. Here's the math part. From that triangle there, that you should probably redraw.
Whoa! And again?
Well, just this little one, right?
Just like a little one? Oh,
It's
that's
up to you. It's up to you. Yeah, just a little.
Big triangle.
No.
From me off guard. Okay.
This is the weight force. Is the gravity weight force always straight down? Yes, that is true. Weight force is always straight down. This little angle here is equal to the angle of the ramp, and we're going to label this Fn, even though it's really the component of gravity that acts perpendicular to the plane.
Is that a whatever degree triangle? Like a right
That,
triangle?
excellent question. That is a 90-degree triangle.
Okay.
In fact, this Fn is actually the component of gravity that acts perpendicular to the plane. Fd is actually the component of gravity that acts parallel to the plane. both long descriptions, we're going to call them FD and FN.
Whoa, whoa.
Just covered up some stuff.
I was, okay.
You were looking for these.
I wasn't, but you can go right there beside the, yeah, perfect. Oh, there's some there, okay, awesome.
How many do we have?
Usually never enough.
We have like 20.
Yeah, that's good. Okay, from that, your basic grade 10 trigonometry. Used to be grade 9, now it's grade 10. Sine of theta. Sine is opposite over hypotenuse, and Steve is right, it's 90 degrees, that's why I can use sine, cos, and tan. So sine of theta is opposite over hypotenuse. Opposite of the theta is my FD, and my hypotenuse is mg, because FW is equal to mg. And when I rearrange that, I get FD is equal to mg sine theta. Your new formula to play with today.
What is
Everyone thought that was the new toy to play with today. They're wrong. The new toy is FD equals mg
So
sine
like,
theta.
why are you not allowed to say that? Like, why are you not
I don't
allowed to
even
say
know.
the name?
I don't even know.
Do they tell you that you can't say it?
Back to physics. What formula am I going to use for Fn?
That's F.
Cos.
Cos theta hata is going to be adjacent over hypotenuse.
I forgot you.
So cos theta is Fn over mg,
Alright.
which tells me that Fn is equal to mg cos theta. Those are your new toys for the day.
I should have put them in front of each other.
You have questions for us?
Oh, we're getting there, yeah. Jonathan's asking which Fn am I calculating here, and the correct answer actually
Oh.
is both, because remember, they are numerically equivalent,
So it doesn't really matter.
right? So when you're calculating this one, it's really equal to that one, just opposite direction.
So it's always the same. Like,
Yeah.
there's two sides to it,
Yep.
but it will be the same.
And the reason that we're going to do this is because today we're going to deal with frictionless ramps, and it's not going to matter, Ryan, but in the coming days, Fn will affect the friction. Think about that as we change that angle. Let me go back to this picture here. Okay? When I'm like this, the friction is, like if I'm trying to move it to the left, the friction is to the right, right? And if I just give it a little bit of an angle, how much friction is there? If you tried to, would it slide down that ramp? Probably not. There's quite a bit of friction there. But as you increase the angle, right, how much friction is there? Less and less. Why? Because this FD becomes bigger and this bit here actually becomes smaller. Right? So the friction becomes less, which is why the steeper the angle, the more likely it is to slide down. Good question.
So what's FD stand for? Another one.
It's just the force down the plane. It's shorthand
Is it
for,
like applied force, but down?
yeah, it's the applied force down the plane. It's shorthand for the component of gravity that acts down the plane, or parallel to the plane. It's my description, FD. Other books will call it F parallel or F8
It
or,
takes a long time to say F parallel.
yeah, that's why I call it FD. It's the force down the plane. Okay, Steve?
I don't even have that.
I'm glad, but still. Okay, so here's a sample problem. I conveniently have placed a 5 kilogram box up a 1 meter long ramp.
Oh.
He doesn't have to.
Yeah, I know. You know what? Students have been, it's so frustrating. Anyway, I want you to find the wave force, the normal force, the force down the plane, the net force down, the net acceleration, time to get to the bottom, and the speed at the bottom.
Is this what we're supposed to use that big triangle for? Because, like, I don't know.
You can if you want, yeah. I don't know, I was just, yeah.
'Cause I don't think I can fit it up there now. Okay.
This triangle doesn't need to be that big.
I'm just making the.
I'll give you a moment while I mark my attendance, and then I will do this problem for you. Okay. Fn, normal force. Okay, so to find Fw, Fn, and Fd, I need to quickly remind myself, I got 30 degrees, 5 kilograms, right? Okay, so the weight force is simply mass times gravity, which you've seen before.
Oh.
5 times 9.8, nothing special here.
And gravity's always 9.8, right?
Gravity is always
And it's
9.8.
not like a negative 9.8?
Oh, great question, Hannah. I'm so glad that you asked that.
I have.
Okay, Hannah's asking, should it be negative?
For a reason I don't think it is, but then it feels like it should be because it's going down.
Yeah, right. Okay, the problem lies, let's go back to this picture right here, right? The problem lies in that down is negative, but are we really concerned with, in this case, is the box going to be moving like, well, I'll have to redraw it so I can move it. Will the box be moving down? No, the box will be moving down the ramp. So the only real directions that I need to concern myself with are up the ramp and down the ramp, and you could say that up the ramp is positive and down the ramp is negative if you want. What I recommend is that you sort of forget about that, right? Straight down is negative, but it doesn't matter here, okay? So in other words, what I'm really saying is that I don't think it matters here, because are we going to use that direction? No.
Okay, so never put a negative.
Well, will it be a problem if you do? No, it won't be. And if if you want to leave it as negative, you go right ahead.
No, so that's good.
49 newtons, right? Okay, now the normal force, Fn, our new toy is, Fn is mg cos theta. We've already got our m and g. It's going to be 49 cos 30. .4 newtons. Again, that normal force is what's contributing to friction. Does anyone remember from grade 11, mu equals Ff over Fn?
Did you say mu?
Mu? Remember mu equals Ff over
I just
Fn?
think mu too.
Yeah. This thing here? Mu equals Ff over Fn. Well, what's the Fn? This guy right here. That's what we're talking about.
This guy. What else are we looking for other than F, like the FW, Fn, and FD?
Well, ultimately, I'm getting to this, right? But I'm showing you the steps to get there.
Okay, well,
What's the FD? Mg sine theta. So 49 sine 30. How much force is accelerating this object down the plane? 24.5 newtons. What's producing that force? What's contributing to it? Where's it coming from? Gravity. And the angle, right? The greater the angle, the greater that FD. If there was no angle, that FD would be 0. Okay, what else do I have to find? A net, time to get to the bottom, and velocity to the bottom. So, I'm going to redraw. There's my FD. Because the motion is up and down the plane, or down the plane, up or down the plane, how many other forces are in that plane that contribute to the motion? Does gravity contribute to it? Well, that's what this FD is, right? Is the object going up like that? No. Is there anything like that opposing that downward force? No, I said there was no friction. So in other words, the net force is equal to the FD. The net force quit is equal to the FD. It's the only force contributing to the downward motion of the box.
So why are you saying A net?
The net acceleration, the overall acceleration.
So net force is?
Yeah, so in other words, F net is equal to MA, and my FD was what value? 24.5.
Why is that equal to 22?
The net force is the sum of all the forces, but we're really only interested in the sum of all the forces in the plane of movement. Right? Like, this normal force isn't contributing to the acceleration. I'm only really worried about the up and down the plane forces. So 24.5 is equal to my mass, which was 5, and so my acceleration is 4.9. Should it have a positive or negative on it? Yeah, because generally negative is straight down and positive is straight up, and this is an acceleration that is in the direction of down the ramp. So you can assign that a positive or negative if you want, or just say, well, it's down the ramp. I think in this case we can all just sort of agree, yeah, well, it's obviously down the ramp, that's the direction it's moving. I'm not going to bother with the sign, but understand that that's the direction that it goes, right? Okay. We'll get to the bottom of this, right? Little joke there. Now I've moved into kinematics here, the time to get to the bottom. Is this accelerated motion or is this constant motion? Can I use V equals D over T? No, this assumes constant velocity. I have accelerated velocity. Time to get to the bottom.
Is that D equals V?
I do know the D.
Wouldn't VI start at 0 because it started at the top?
VI starts at 0. Do I know VF?
Yeah, no.
What do I know about this? I know it's 1 meter, right? If I've got the acceleration, I have the VI was 0. Do I know the VF? No, that's what I'm trying to get here, right? How am I going to get the time to get to the bottom?
Oh, you don't have to. Wait a minute. No, I'm just not able.
How am I going to get the time to the bottom?
Can you D equals D over T?
D equals VIT plus a half AT squared will work, right?
So we don't.
Yeah, because I have the D, I have the initial velocity, I have the acceleration, I don't have the time. What's the distance? 1 meter. The initial velocity is 0 times t is 0. Plus 1/2, the acceleration is 4.9 t squared. One half of 4.9 is 2.45 t squared. So t is equal to 1 divided by 2.45, and take the square root. Can someone do the math for me?
0.6 for
0.6?
yeah.
Okay. How about the velocity at the bottom?
What's the next question?
Yeah, that's part F, I guess.
You could do
VF equals VI plus AT. 0 plus my acceleration of 4.9. My time is 0.6. You'll have to tell. Oh, I got a calculator here.
Which ones are square? Oh, that's the two ABs.
Yep.
Uh,
2.94 meters per second. Okay, so what's new here? Really just this bit right here, which leads you into the net force, right? That's all that's really new. These two guys need to appear on your cheat sheet.
What was the, can you go back one? Lost it. Okay,
Yeah.
good.
Okay, a couple of parting comments here, and then I'll give you some questions to work on. Note that on a frictionless surface, F net is the, I'm going to leave this up here, so don't write it down, just watch. Just watch for now. On a frictionless surface, the net force is equal to FD. This means F net is equal to MA. FD is equal to mg sine theta. So on a frictionless surface, the mass doesn't matter, and the acceleration is equal to g sine theta.
Just write down that equation, that formula.
But this is only true on a frictionless surface. On a frictionless surface, the mass does not matter, and the acceleration is g sine theta. Just great, isn't it? Alrighty, I will stop there. There are some textbook questions if you wish. I have a handout as well with a QR code and everything. My plan is to talk about friction a bit tomorrow, and I will give you Friday's period to do some work and do some practice, because I know I need to do that. That is all for today.